Okay. So today we're going to do a calculation, which is the calculation of entanglement entropy in 2D CFT using the Replica method. So this calculation brings together basically everything that we've talked about this semester. I know we've been kind of jumping around, doing different things. This does everything is here, except gravity. We're going to bring gravity in later. But this really is one of my, so this is based on a paper of Cardi and Calabrese from the early 2000s. The result was known earlier than that. This result we're going to derive on the entanglement entropy was known 10 or 20 years earlier. But this calculation is really just lovely. So this is like one of my all-time favorite papers. So the goal is the following. We have a 2D CFT. Let's say it's a CFT on the real line, although by conformal transformations it doesn't really matter. It could be on a circle. So space is the real line. Region A is a connected region, which in 1 + 1 dimensions just means that region A is an interval. And we're going to be working in the vacuum state. Rho is 0, 0. And our goal is to find S of rho A, the von Neumann entropy of region A. And we're going to do this by the replica method. So the replica method is as follows. So the von Neumann entropy of a density matrix is minus trace of rho log rho. I'm going to put hats on these rho to indicate that they're normalized, okay? Because I'm going to also talk about non-normalized ones. So rho hat is equal to rho over trace rho, where rho is unnormalized. So the idea of the replica trick is the following. Logs, there's no path integral that calculates the log of an operator. But there are path integrals that calculate the power of an operator. Okay, so the idea, well, this isn't just used in path integrals, but for our purposes, that's why it's useful. So the idea is to consider a replicated system where you have n copies and calculate trace of rho to the n. And if you can calculate trace of rho to the n, then, well, so the normalized version of that would then be z, trace of rho hat to the n would be z of n over z of 1 to the n. And then just using the fact that rho hat to the 1 plus epsilon for small epsilon is rho hat plus epsilon rho hat log rho hat plus dot dot dot. We're going to use these powers to extract the log. That is S of rho, the von Neumann entropy that we're looking for, is formally minus dn z of n over z of 1 to the n of evaluated at n equals 1. Now, these formulas that I've written here make sense for non-integer n. Like the trace of, you could take an operator and you can raise it to a non-integer power. That trace would then just be the sum of the eigenvalues to that non-integer power. There's nothing wrong with that. When we actually go to calculate this, we're going to calculate trace of rho to the n by thinking about the density matrix of n copies of the system, and then, of course, n needs to be an integer. So the way we're going to do this calculation is by finding a path integral that calculates this in integer n, and then analytically continuing away from the integers to find the answer at non-integer n, and then taking the limit of n to 1 to extract the log. That's the strategy. So is that clear? Indeed.
And you're just assuming that like whatever functional form you write down for the integers is the same as it is for non-integers.
That's true. Yeah, so let me. Right, so there's a function that vanishes at integers, as you say, and therefore when we analytically continue away from the integers, we have an ambiguity, which is the ambiguity of adding functions proportional to sine pi x. So there's two ways that you can get around this problem. I hesitate to say this on video. There's two ways that you can get around this problem. One is that there's a theorem whose name I can't remember right now. What? That sounds right, yeah. That under some conditions on the asymptotics in the complex x-plane, that this analytic continuation is unique. Okay, so like sine pi x is exponentially large in the upper half plane, and basically any such function is exponentially large in the upper half plane. So if you impose some boundedness on the complex plane, or if you can demonstrate that your function has some nice properties on the complex plane, then your analytic continuation is unique. That's one way to do it. The other way to do it is just write down something reasonable, do the continuation, and then check if everything is reasonable. And in practice, that's how we do it. I actually don't, the calculation that we're about to do, I actually don't know whether the assumptions of the theorem have been carefully checked in this case. It was not done in the original paper of Cardi and Calabrese, and I've never seen the calculation. Maybe someone has checked it. But in practice, we're just going to do the obvious analytic continuation, and when it gives us a reasonable answer, we're going to be happy and move on.
You're talking about the complex n plane?
Yeah.
Why would we want something bounded in the complex n plane?
Well, it's not that we want it. It's if the thing we're calculating is bounded, if you can prove that trace of rho to the n has nice properties in the complex n plane, then you have a unique way of doing your analytic continuation. I think that has been checked for some like free field calculations. I don't know of anyone checking it for the interacting conformal field theory calculation we're going to do today. So this replica calculation is often phrased in terms of what's called the Renyi entropy. So the Renyi entropy is, by definition, Sn is 1 over 1 minus n trace log rho hat to the n. And so that's just it's just a repackaging of my z of n over there. So z of n I call the replica partition function. Sn is the Renyi entropy, which is a more standard terminology for exactly the same quantity. And the von Neumann entropy, S of rho, is the limit as n goes to 1 of Sn. So another way of saying it is that we're going to calculate the Renyi entropies at integer n, then we're going to analytically continue the Renyi entropy to extract the von Neumann entropy.
Shouldn't the log be?
What? Oh, is that backwards?
Yeah, log.
Yeah, thank you. Log trace. Yeah. Okay, so the hard part of this calculation, the bulk of this calculation is to calculate trace of rho to the n. And for now, we're going to think of n being an integer, but there's just going to be an n in the final answer, and we're going to then continue in the obvious way. Okay. So region A is the, let's take this to the interval between z1 and z2. So we're thinking of the Euclidean spacetime R2 as the complex z-plane, as we often do in conformal field theory. So on the complex z-plane, this is our Euclidean space. The real axis is time 0. And z1 is here. z2 is here. So this is region A. And we talked about how to use a Euclidean path integral to calculate rho A. So let me remind you what the path integral expression was for rho A. It's the Euclidean path integral with a cut on region A. Should I remind you where this equation came from, or do we remember this? Maybe I can remind you quickly, and then you can tell me if I should remind you more slowly. Okay, so first of all, what does this picture mean? Rho A is an operator that you can think of as, it's an operator on region A. So you should think of this as accepting inputs, which are field data on region A. It has two legs for the bra and the ket. And those two legs correspond to the field data that you put above and below this cut as boundary conditions on your Euclidean path integral. And so that's what this picture means. Now, let me remind you where it came from. Well, the vacuum state was the path integral on the lower half plane, because the Euclidean path integral damps any excitations and projects us onto the vacuum state. Okay, and then the vacuum state density matrix was therefore just two copies of the path integral on the lower half plane that I've suggestively put next to each other. And then so if we call this
Oh, it isn't recorded.
That's okay. If we call this region A and the rest is A complement, then the trace over A complement, so when we trace over A complement, that just glues A complement together. So this part gets glued together, and we end up with the path integral with a cut on region A, which is exactly what I told you a minute ago for the density matrix operator. Okay, good? Questions? Therefore, now I'm going to write down the path integral for trace of rho A to the n. So this is just rho A times rho A times rho A times rho A. Okay, so that as a path integral is n copies of trace is n copies of rho A. So let me draw that this way. Okay, so that's n copies of rho A, but these are matrices, and we're multiplying these matrices. Okay, so the matrix multiplication means that we put the same index, or we stick the same field data on the two rows and then sum over it. Okay, that's the contraction of indices in the matrix multiplication. So what we're really doing here is we're gluing these cuts together. So the bottom of this cut gets glued to the top of that cut. What this arrow means, you can interpret this. Well, let me draw more arrows and then I'll interpret them. Okay, so the bottom of this cut gets glued to the next one, and so on. And then the fact that it's a trace means we put the same data on the left and right and sum over it. So that glues the bottom of this last one back to the top of the first one. Okay, so there's two ways to think about what these arrows mean. One way to think about it is in terms of boundary conditions on the fields. Okay, so we have some quantum fields living on each of these planes, and we put a boundary condition on each of these cuts, but we put the same boundary condition at the bottom of this cut as we do at the top of this cut. And similarly, for all the other gluings, we put the same boundary conditions on the glued cuts, and then we sum over those boundary conditions. Another way of thinking about it, which is a more geometric way of thinking about it, is just to say that we're gluing the manifold together. So we're really considering one big crazy manifold, which you get by gluing all these things at the cuts. So like if I'm walking along and I walk through here, I'm going to come out there. I think I did it backwards. Sorry. If I'm walking along and I get to here, I'm going to come out here. And then if I keep walking and I get to here, I'm going to come out here. If I keep walking to there, I'll get back to where I started. questions?
This is like the homework problem that you just gave us.
Yeah, the homework problem was various warm-ups for this calculation that we're doing today. Okay. Does that make sense? Should I write a formula for this path integral? I mean, we're going to calculate it, but I could write something a little bit more explicit. So it's a path integral d phi 1, d phi 2, dot, 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 d phi n. Those are all the quantum fields living on the n sheets. E to the minus s CFT of sum over n of SCFT, or sum over k of SCFT of phi k, with the gluing conditions that say phi 1 of z in A minus is equal to phi 2 of z in A plus, etc. Okay, so we're just doing that path integral with these boundary conditions that glue the sheets together. Good? All right, let's do this crazy path integral. Yeah.
We know the expression for rho A in terms of the modular Hamiltonian, right?
Yeah.
So we could also in principle calculate the entropy using that expression. Is it?
I don't know of any way of doing the calculation that way. It seems like it should be possible.
So what are
but
we
I tried
missing?
it once and I couldn't get it. So I think it's just subtle with dealing with it. I think there's a subtlety with dealing with the vacuum subtraction and the UV divergences. I think it could be done if you're very careful, but it doesn't make the calculation trivial.
So we have to regularize this expectation value of this distance. Is that?
That's yeah. I'm trying to remember. I guess so. I don't know. I've never done the calculation. I don't know how to do the calculation that way. It should be possible.
Yes.
Okay, so one way to proceed, and actually we're not going to quite do it this way because it's a bit hard. I just want to illustrate that that this is basically a conformal transformation. Okay, so basically we're going to do this path integral by a conformal transformation. I'm going to first say a very direct way of doing it, but we're not going to use that way. So remember that in a 2D CFT, the path integral on any manifold, on any metric, is the trivial one with the regular flat metric times e to the minus the anomaly action of Polyakov, the Liouville action that we wrote a couple lectures ago. So in principle, we calculated the path integral on an arbitrary topologically trivial manifold. I guess this manifold, well, as we're going to see, this manifold is topologically a sphere. So this formula would work in principle. Now, what is G mu nu for this crazy manifold that I just drew a picture of? So on the replica manifold, G mu nu is almost delta mu nu. I mean, at no point did I say we're gonna like turn on curvature. We were just studying a CFT in flat space. Okay, so you might think, isn't the partition function on this just obviously 1, trivial? But that's not quite right, because the metric is only flat except at the gluing points, Z1 and Z2, where these manifolds are glued together. So in fact, there's curvature at those points. By gluing the manifold, we've introduced some curvature. And this is something that you did on the homework. So these points are conical excesses. So a conical excess just means the following. A small circle of proper radius r has circumference 2 pi n r, where n is bigger than 1. That's what makes it a conical excess. So how do we see that? Well, I've already drawn the picture. If we consider a circle centered at this point here, this is one of these defect points, then if you're an ant walking around on this manifold, then we said that if you walk this way, you're going to come out down here, and then here, and then here. So you have to go around 3 times further. Well, in this picture, there's 3 sheets. So you have to go around n times 2 pi in order to get back where you started. And that means that this manifold is not flat. Even though we started with a flat manifold, we've introduced some curvature. And that curvature contributes to this Polyakov action and gives you a non-zero partition function. Now, this way of doing the calculation is doable. Okay, so you could do the calculation this way. You can. It's tricky because these are singularities. So you have to smooth out the singularity. You have to understand how to regulate that singularity. But if you do that very carefully, you can plug it into this formula and get the right answer. We're not going to do it that way. We're going to use the word identity because it's much easier.
But isn't it the same thing? Like, word identity, so this is like the integrated version of the word identity.
Yeah, it's the same. It's just the steps in the calculation look totally different.
Oh,
it's the same though. Yeah.
How do you, if you were to do it this way, how do you handle the fact that the curvature is singular or something like that?
You have to regulate it. So what you have to do is you have to take this pointy, you have these, well, I don't know how to draw a conical excess. I could draw a conical defect. So you have these pointy spots, and what you have to do is cut out little circles of size epsilon, and you take those circles and you cut out the manifold you cut out the manifold there and you replace it by something smooth. And the answer that you get will now depend on your regulator. It will depend on how you cut out those singularities. But that will just go into the UV divergence of the entanglement entropy. It's supposed to depend on the regulator, so it's okay. And the answer we get by this other method will also depend on the regulator. What we're going to do instead, let me just jump ahead because I'm going to say this many times over the next couple weeks, but I'll say it for the first time now. In gravity regulates it for you. Okay, so and this was also hinted at on the homework. So in quantum field theory, you get these pointy spots when you calculate entanglement, and those give you UV divergences, and you have to regulate them, and things are UV sensitive. But when you couple a quantum field theory to gravity, gravity doesn't let you stick singularities in places because they don't satisfy the Einstein equations. So as I hinted at on the homework, this pointy manifold does not satisfy the Einstein equations. So when you couple a quantum field theory to gravity, it actually does this smoothing for you because the manifold back reacts and smooths things out for you. And this will be reflected in the entanglement structure of quantum gravity, and the fact that entanglements in quantum gravity are UV finite. That gravity itself does the regulating for you and gives you finite answers. So they're not, you lose the UV divergences, but you get extra contributions from gravity at the tip. And that's going to be crucial in a week or so. Okay, let's go back to quantum field theory. So the trick that we're going to use instead of this Polyakov anomaly action, we're going to do what's called uniformizing this manifold, which just means to find a conformal map to the plane. Well, more generally, uniformizing is a problem of finding conformal maps. For this case, we can map this to the plane, as we'll see in a second. Yeah?
So based on what you said, why should you ever have any singular manifold in GR? Why don't all the singularities that occur with each similarities get resolved?
Yeah, that's a great question. So it's the difference between time evolution and Euclidean solutions. So I think in Euclidean we're doing Euclidean path integrals, and in Euclidean gravity, you don't include singularities because you have to solve the equations of motion, and gravity won't let you have singularities. The reason that we do have to worry about singularities in GR is because you can start with a solution that has no singularities, evolve it in time, and now it has a singularity. So those can't be avoided. That's like black hole singularities. But there's a difference between the singularities that are unavoidable because they come from time evolution, and singularities like this one in a Euclidean manifold, which just won't appear by the equations of motion. Now, the black hole singularity also violates the equations of motion, but it's unavoidable. So it's not that we get to drop it; it's that the theory is breaking down.
So you mean pure gravity in Euclidean signature won't admit this solution, but if I include like matter?
Yeah, if you include matter, then you can have solutions like this. But yeah, pure gravity.
Pure gravity.
I mean, is this the statement that if you look at a black hole solution and you maybe stick in terms of caps off at the horizon, that's it?
Yeah, it's related to that. It's related to that. Yeah. Well, we're going to get to it, but this in gravity, this is going to be like the Euclidean horizon. Okay, so what does it mean to uniformize? Well, in this case, the statement is that any topologically trivial two-manifold without boundary can be conformally mapped to the plane or sphere. It's in our case, I'm being a little bit quick about the points at infinity. But in conformal field theory, we can always, every time I draw a plane in conformal field theory, you can think of it as a sphere, just by including the point at infinity. The map. For this crazy manifold, I'm going to derive in 2 steps, but you've already seen it on the homework. So the first step is to set y equal to z minus z1 over z2 minus z. So this is step 1. So let me draw a picture. Okay, I'm going to stop drawing these crazy pictures with n sheets. I'm just going to draw one of the sheets. Okay, so on the z-plane, which was our starting coordinate, region A went from z1 to z2. Now, under the map that I just defined, we go to the y-plane. And what that map does is it takes z1 to the origin and z2 to infinity. That's how I came up with that map, or how someone else came up with that map. So now region A looks like this. It's just the positive real line. Okay? And so that was step 1. And then step 2 is to define w equals y to the 1 over n. So the way to think about this is the following. We had n copies of this, and we want to squeeze those all onto one picture. So we take the nth root. Okay, so this takes us on the w plane to just one copy of the w plane, where now w is y to the 1 over n, which is z minus z1 over z2 minus z to the 1 over n. And I'm going to draw this picture for n equals 3. So for n equals 3, it looks like this. So this is region A, this is also region A, and this is also region A. So we've taken the cube root. This first patch of the W plane corresponds to the entire Y plane. But the point is we can now go through the cut on the Y plane, land on the second sheet, and that's the second wedge on the W plane. Okay, so the first 2 pictures, there were sort of n copies of the first picture. There were n copies of the second picture. But in the picture on the W plane, there's just the W plane once. It's covering the entire manifold. So the W plane is this picture, and this is that crazy manifold that we started with. Does that make sense? Maybe I can put an equation that explains this a little bit. So, like for example, let's look at one of these curves. Let's look at one of these loops. Say a small loop around the defect at point z1. That loop corresponds to taking z minus z1 and multiplying by e to the 2 pi I. You should think of this as following the curve, where you multiply by a phase, and that phase runs from 0 to 2 pi. And if you plug this in to the w coordinate, then you'll see that that corresponds to taking w to w e to the 2 pi I over 3. So on the w plane, that curve looks like this. So at this point, we've now successfully uniformized our crazy manifold. That is, we've mapped it to just the plane. Any questions so far? Okay. Now, what we're going to do is we're going to calculate the stress tensor on the crazy replica manifold. Let me tell you the strategy. So the word identity, well, I'm going to write a detailed equation in a minute, but our goal is to find the partition function. We're going to first calculate the stress tensor, and from that back our way to the partition function, because using the ward identity. So we want to calculate the stress tensor on the replica manifold. The general relationship between Weyl and conformal transformations, which I remind you, I posted these notes on the web page that go through this super carefully, where all the primes go and the relationship between conformal and Weyl, and just getting everything very carefully. So the formula that we talked about and that you can find in those notes is the following. O of x in the metric omega squared dx squared, which is the metric dx prime squared, is equal to O prime of x prime, dot, 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 in the metric dx squared. So this is for the case where omega is dx prime dx to the 1 over d. So we're talking about Weyl transformations, but Weyl transformations which, so Weyl transformations, we're changing the metric there's two different metrics here, but it's a special Weyl transformation that can be realized as a diff. So it's a Weyl transformation that can be reinterpreted as a conformal transformation. So this is the formula. I had this up before, and you can find it in those notes. We're just going to use it. So in our case, the right-hand side of the formula, you're going to think of this as the metric dw squared. So so on the right-hand side is the w coordinate, the w plane, and on the left-hand side is the replica manifold. So this is going to be our replica manifold. That is that crazy z-plane thing. So this will be equal to dz squared on the left. So what this formula says for the stress tensor is that T of Z on the replica manifold with the metric dz bar is equal to T prime of Z on the W plane with the flat metric on the W plane, where you should think of Z as W prime in this formula. Okay, so what does this formula say? It says that if we start on the W plane and do the conformal transformation from W to Z, that gives us the answer on the replica manifold, which is the one that what we're really interested in is the left-hand side. And we're going to do that by starting in the W and then doing this transformation. We also derived the conformal transformation of the stress tensor. It says T prime of Z is dW dZ squared times T of W minus C over 12 times the Shortchian derivative W comma Z. Which I think you calculated, and the answer is W prime of Z squared T of W plus C over 24, 1 minus 1 over N squared, Z1 minus Z2 squared over Z minus Z1 squared, Z minus Z2 squared. So that's what you get when you take this map and you plug it into the formula for the Shortchian derivative, which was on the homework. So that's the conformal transformation of the stress tensor. Now we're going to evaluate its expectation value. In order to apply this formula, we just need to take the expectation value on both sides. Now, T of W in the metric dW bar, that's the first term. So for the expectation value of this, that's just 0. Because in the vacuum state, in a thermionic flat manifold, in the vacuum state, the stress tensor just vanishes. Okay, so that term is 0. And now we basically have our answer for this part of the calculation. It's just the second term. Okay, so what we've found is that T of Z on the replica manifold is equal to, I'm going to write this as 1 over N times H sub N Z1 minus Z2 squared over Z minus Z1 squared, Z minus Z2 squared, where Hn is defined to be C over 24 times N minus 1 over N. So let's recap. That crazy manifold with all the sheets has some curvature at the defect points. Because of that curvature, that creates some energy in the conformal field theory, and So T, the expectation value of the stress tensor is not 0 on that manifold, and we calculated it, here it is. Okay, that's sort of an aside for now. Let me remind you that we calculated T of Z with 2 operator insertions. Two scalar operator insertions. On the plane with the metric TZ, DZ, DZ bar. So we did this calculation when we were discussing the word identity. We did this as an example of the word identity. Let me remind you how it went. We used the conformal transformation properties of O to read off the singular behavior. And then we said, well, this is an analytic function. It's completely determined by its poles and singularities. And we found the whole function. So let me remind you what we found. We found that this is H, the scaling weight of O, times Z1 minus Z2 squared over Z minus Z1 squared, Z minus Z2 squared. So what we've just shown over there is that up to a fitting factor of 1 over n, which I'm going to explain in a second, we've just shown that putting a cut. Okay, so you start with the z-plane, and putting this cut here. In other words, taking n copies and gluing them all together on this cut. As far as the stress tensor is concerned, is the same as inserting some local operators at the endpoint of the cut. It's not literally the same. It's just the stress tensor sees it the same way. Okay, so the experience of the stress tensor is that these two things are the same. People call these things twist operators. Okay, so because the endpoints act like operators, we can just declare them to be an operator called a twist operator, and then people refer to this as the correlation function of twist operators. But it's just defined by exactly what the calculation that we just did. That 1 over n is a difference, and we're about to see where that came from.
Tom?
Yeah.
So is that like, it should be the ratio of that 3-point function to the 2-point function, right? Which is equal to that, what you wrote on the right hand side. Yeah.
Yes.
Because that is not dimensionally correct.
The 2-point function is also
Oh, I see.
metal trash. There's a power
Yes.
metal trash. The 2-point.
Yes, thank you.
Yeah, times the 2-point.
Yeah. Thanks. Okay. Okay, we're almost there. We've calculated the stress tensor, but what we really want is the partition function. We're going to extract that using the word identity. the ward identity, again, this is a formula that we've seen. Says d by dz1 log z replica is equal to n times the residue of z near z1 of t of z on the replica manifold. So we have seen this formula. I didn't write it quite this way. I wrote it in terms of correlation functions. But this left-hand side here is just 1 over 1 dz1 of 1. Okay, so because the partition function is the expectation value of 1. Okay, so we talked about correlation functions, but the same thing is true for partition functions. So in fact, we did see this formula. On the right-hand side, the only difference from the formula that I wrote earlier is that there's an n. The origin of that n is because of the n sheets. So in other words, when we take this derivative with respect to z, we're not just changing, so let's draw the n sheets. We really have a z1 on each sheet. And when we take this derivative, we're moving the point z1 on all n sheets. We're moving this one over, we're moving this one over, we're moving this one over. So the derivative with respect to z1 picks up a contribution from the stress tensor on each of the n sheets. But they're all equal. So you just get an overall factor of n in the ward limit. Are you convinced that I showed you this formula before? We said that, so the way I wrote the formula before was that the conformal, so the way let me remind you how I wrote it before. I said that the conformal transformation of some observable, I wrote it as an operator, but the conformal transformation of any observable in a 2D CFT is determined by the residues where the current, in this case the stress tensor, that generates that conformal transformation, where that hits the observable. Okay. Determined by the singularities, the correlation function of t with O. Does that sound familiar?
So you're sort of skipping a step where there's a conformal transformation which just moves Z1.
You mean on the first sheet? See, the problem is I didn't even really give it a name. If there's really a Z1 parentheses 1 and like a Z1 parentheses 2, and when we're moving all of them, and they each give a residue. Yeah. Let me, since I'm getting some half blank stares, let me try to write the formula that we had before. So the conformal transformation of some observable is equal to the residue, well, it was equal to the, I won't get all the indices and everything right, but it was equal to hitting it with the charge, which is some correlation function where you put in the current, which is T zeta. And if the operator is local, then this was just the residue well, let's make it a local operator. So it's O, let's say it's O of Z1. Then it's the residue of Z near Z1 of zeta of Z, T of Z, O of Z1. Okay, so this formula I wrote before, and now I've just applied that formula to the unit operator, but on a funny manifold, which makes things depend on Z1. Okay, so dz1 of z replica is that residue over there. So we've calculated the stress tensor, and we just need to take the residue. Taking the residue of this expression gives you minus 2hn over z1 minus z2. That's the residue of this answer we got for the stress tensor. You can do the same exact formula with bars. dz1 bar of z replica is minus 2hn over z1 bar minus z2 bar. And you can do the same thing for dz2 and dz2 bar of z replica.
Bar to 1 to Z1.
What?
DZ1, DZ1 bar instead of D bar Z1.
It's the same thing. It's the same thing. And now you can integrate this. So now we have a differential equation for z replica, and we can integrate that. And that's easy to do. And the result is z replica is minus 4hn log z1 minus z2 absolute value plus the integration constant. Exponentiating.
Some those are all logs, right? Derivative of log.
Yes. Sorry. Log, 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 log. So now we can exponentiate, and z replica is equal to trace of rho to the n, trace of rho a to the n is equal to an unknown constant alpha n times z1 minus z2 absolute value to the minus 4 hn where hn was defined before. Yeah.
You said before that there would be some sensitivity to UV divergences.
Mm-hmm.
Where was that?
It's coming, but it's in alpha n.
Okay.
So, let's see. So alpha n is undetermined because it was this integration constant. But alpha 1 is equal to 1. And let's see if I can, let's see. So that's because that should come from trace of row A is equal to 1. Now I'm getting confused.
No, row A is unknown.
Yeah, so.
Trace of row A hat
Yeah.
is equal to 1. So trace of, because, wait, how did I get that?
Well, hn is 0 and it equals 1.
Ah, good, right. Yeah, hn is 0, so this term drops out. And so,
And so you get 1.
well, let's see, sorry. Here I've written trace of row. I've defined this alpha in terms of trace of row as opposed to row hat. So actually, I think I've made a bit of a, I think I mixed up my notation a little bit. The alpha, this alpha does not have to be 1, but we can fix the value of, well, we do need the normalized thing to be 1. Okay, so we're going to use that in a second. So I had my normalizations
But is the thing that
mixed
we're,
up a bit. What? I'll write the last part of the calculation and then we can look at this normalization. So the entanglement entropy is then, well, first let's look at the Rennie. So the Rennie was 1 over 1 minus n log trace row hat to the n. Okay, I messed up my hats, so let me redefine my notation slightly, and that way my formulas will be correct. So trace of row hat to the n is, let's call this alpha n hat times z1 minus z2 to the minus 4hn. Now this alpha hat n is unknown, but alpha 1 hat is equal to 1. That's what I was. That's what I should have said before.
you could also just say that since you know that like row A is proportional to row hat, and you know that that constant of proportionality is alpha 1.
Yes. I think that's equivalent to what I just said. Yeah. I'm just doing it this way so I can write the next few formulas without messing it up. So this we can now just plug in. So this is 1 over 1 minus n times minus 4 hn log absolute value z1 minus z2 plus log alpha hat n. And so the von Neumann entropy S of row A is S is the Rennie in the limit n goes to 1. Now hn goes to 0 as n minus 1, but there's a denominator here. Okay, so these are going to cancel, and you're going to get some finite von Neumann entropy. So you can just plug in this hn and take that limit, and you find S of row A is C over 3 log absolute value z1 minus z2 plus constant. Now, the way we always write this is by absorbing the constant into the log. Now, just by dimensional analysis, this has to be, so logs need to have dimensionless arguments. So just by dimensional analysis, there has to be a UV cutoff showing up here. It's a conformal field theory. There are no dimensionful scales except the UV cutoff. So the way we write this formula is S of rho A is C over 3 log absolute value Z1 minus Z2 over epsilon, where that's the UV cutoff. And that is our final answer for the entanglement entropy in the vacuum state of a 2D CFT.
Can you say that last bit again?
Yeah. We're going to absorb this constant into the log. By dimensional analysis, it has to be the UV cutoff. Now, it could be like 3 times the UV cutoff, but the point is that numbers like that are scheme dependent. They depend on how you regulate and how you define the UV cutoff. So really, you should think of the denominator here as being scheme dependent. And if somebody comes along and says, no, that's 2 epsilon, well, that's the same formula. It's just a redefinition of the cutoff. So what's really meaningful about this formula is, first of all, that there's a logarithmic divergence. That's a meaningful fact here. You can't talk about like whether it's epsilon or 2 epsilon. And secondly, the coefficient of the log term is C over 3. That's also physically meaningful. So like no matter what I do to the UV cutoff, it won't change the fact that the log is proportional to central charge over 3. So everything except the denominator here is a physical prediction. The denominator is scheme dependent, but the rest is meaningful. And if you had done the calculation the other way, so remember I talked about taking the cone and cutting off the tip of the cone with a cutoff epsilon. You can do that calculation and you get exactly the same answer. Then you actually get an epsilon there, which will roughly be the size of the region you cut out. Of course, the exact details will depend on exactly how you cut it out. Did you replace it by like how smooth was the thing you replaced it by, and how big exactly was the thing you cut out? All that stuff gets absorbed into the UV cutoff.
There wasn't really any way to see without using this like dimensional analysis argument that these integration constants had anything to do with UV divergences.
Well, I think in the way we did it, using the word identity, I don't think that there was any way to see it other than dimensional analysis. But if we had done it using the anomaly action, then we would have seen very clearly that it was the UV cutoff that we used to regulate the tip of the cone. Yeah.
The dimensional analysis argument would say that that term has to have something dividing Z1 minus Z2 anywhere, right? Even before you absorb the constant.
Well, if the constant is log epsilon, then no. So basically that's what's happening, is the constant has a log epsilon in it. Any questions? Yeah.
So physically, what this formula is telling us that only modes with wavelengths lying between the cutoff and the length of the interval contribute to entanglement. Is that the right way?
Yeah, I think that's exactly the right way to think about it. Yeah. There's sort of, yeah.
So the length of the interval is basically like an infrared cutoff for the mode.
Yeah. Yeah. Yep.
So this formula is like log of IR cutoff by UV cutoff.
That's right. Yeah. Yeah. All right.